While we set up, once again, I'll take advantage of the setup time to introduce our next speaker. Next, we're lucky to have Professor Rothenhäusler from Stanford University. He received his PhD from ETH Zurich and, in fact, spent a little bit of time here doing a postdoc at UC Berkeley. He was recently awarded the David Cox Research Prize by the Royal Statistical Society and is one of the founders of the online Causal Inference Seminar. We were actually lucky to see him speak this year at the Joint Colloquium, so he'll be speaking today on a formal framework for the stability principle in veridical data science. And let's give a warm welcome to Professor Rothenhäusler.
Thank you. Thank you for the very nice introduction. It's great to be back. Sorry for the delay. Yes, so this was work with Eugene. She's a PhD student at Stanford who has done fantastic work. So just brief outline, what we're trying to do is we're going to try to build a suggestion for some theoretical foundations for stability analysis as advocated for in veridical data science. And yeah, just for I was first introduced to these ideas when I started my postdoc with Vin, I would say 5 years ago. And this is a whole philosophy, and there's one part of it that really started got me thinking, and that part was the stability principle. The stability principle here, there's one quote, the knowledge that data scientists can extract from analysis is limited to conclusions that are stable across appropriate choices. So here it means for example, maybe we want to change the way we do the pre-processing, maybe we want to change the way that the model is specified, maybe we want to change the errors, maybe we would want to use procedures that use different identifying assumptions whatsoever. In causal inference, for example, you could have one data set and maybe there are multiple approaches that seem reasonable to you. So maybe you have one variable that you might think might be an instrument. Maybe there's a regression adjustment that you could run. But what I was starting to think about was okay, well, if we don't have a theoretical model, then it's kind of hard to reason about how exactly we should do this, right? So what is a good way of running a stability? What is maybe a bad way of running a stability? How should we choose these multiple approaches? How should we aggregate them? And how should we report uncertainty? And the main challenge is that we do not really know the structure and the strength of the biases of these different procedures, so we don't really know how to aggregate them. We can't just simply use a random effect model. Okay, and there's one particular suggestion that we have, so we'll talk about that now. And we're thinking about it from a distribution shift perspective. So let's say if you want to estimate a statistical parameter, here written as a risk minimization problem, maybe GLM. Now you have some data, and maybe due to some reasons, you don't get data actually from the distribution that you want to sample from, but maybe when you set up your study, there are some subtle mistakes that you make and you sample from a slightly different distribution. We will call this perturbed distribution here, P xi. So this is P naught is the distribution that you're interested in. Maybe due to some random mistakes that are made, you sample from something slightly different. Now that's your estimator. So in the end, you will have two sources of uncertainty when you compare to the target that you're actually trying to estimate. And in the end, what we want to do is we want to quantify both of these types of uncertainty, obviously. And so what is a good model for this distribution shift, right? And there are lots of proposals in the literature, of course. I think the most common one is covariate shift, where you assume that the covariates change and then y given x is invariant across setting. There are other types of assumptions that are similar. I call all of them sparse distribution shift model because they assume that the shift only affects some part of the data and leave other parts of the data invariant. But maybe when you're thinking about replication study, maybe it's not a sparse shift because these people usually all try to do the same thing, right? They have the same experimental protocol. They try to kind of recruit the same people. So maybe there, the changes are more millions of tiny small changes. None of them large enough for you to notice, but all of them kind of, aggregate. And that is the final kind of change that you see. And that's what I would call a dense distribution shift. So not one large thing that changes a lot, rest invariant, but tiny millions of small changes that kind of that aggregate. We also, at this stage, you could also model shifts as in a worst case setting, so minimax type of approaches. But because people are really trying to do the same thing, I don't think nature is trying to be adversarial between what's happening here and let's say at Harvard. So that's why we want to model shifts as random. Okay, So here now, this is a bit of a toy model. This toy model will have some consequences later on and a certain CLT. And I think that CLT can be justified also in different ways. But for now, let's work with this toy model. So we start, let's say, with a uniform random variable. You can do more general cases too. You take a bunch of bins and let's say maybe like m different bins. And now you just take a random variable and you randomly upweight and downweight events. So maybe, for example, you get more older people, the old people are randomly shifted upwards, and maybe, someone who's doing sports get like slightly randomly downweighted. So you're just like, there are tiny small changes that kind of either increase your probability or decrease your probability. You can also do this for multivariate distributions, in which case you just take a density, you create bins, you randomly upweight and downweight. Okay, so how is this different from other models? People often worry about overlap. So that means that on one distribution, you have a different support than on another distribution. These weights, they can be 0. So that means essentially here you can have random overlap violations. So compared to an adversarial overlap violation, here just randomly parts of your overlap might shift. People also often worry about a shift in y given x. Here, if you include y in this random reweighting, then of course also the distribution of y given x will change randomly. We don't use worst case bounds. You can also ask, how is this different from meta-analysis? In meta-analysis, you usually have a lot of data sets, right? So here we're building a distribution shift model. So what we're trying to do is we're trying to use structure where we just have 1 or 2 data sets. And essentially what we're going to do is we're going to use these multiple estimators to kind of try to mimic some sort of meta-analysis on a single data set, for lack of a better term. Okay, so now let's do some theory. What you can do is, like, if you take limits, you make like these buckets smaller, random shifts. At some point a certain like distributional CLT kicks in. And what that means concretely is if you take means of functions of random variables, you aggregate over your data set, that still follows a Gaussian distribution as under IID sampling, but you get a variance inflation factor. So under IID sampling, you get a 1 here, but because of this additional random like upweighting and downweighting, you get some inflation factor here. And the problem is that in practice, you don't know how large this inflation factor is, so we will have to estimate this from data. You can now ask, is this actually appropriate in practice? Does it have any connection to reality? So what you can do is you can take this distributional CLT and like build some diagnostics on top of that. So for example, you can take 2 replication studies, look at the difference in means, standardize it a little bit. And what this distributional CLT says, like, well, this still follows a Gaussian distribution just with inflated variance compared to IID sampling. So here's an example from a replication study. To check Gaussianity, we look at QQ plots, right? So now I'm looking at the QQ plot here. In usual QQ plots, each point is one observation. Here, each point is a difference in means for different covariates and outcomes. And at least on this side, we're like super happy to report that the shift looks Gaussian to me. So it's on a line. The red line is what you would see under IID sampling. So you see larger shifts between the 2 replication studies than what you would observe under IID sampling, but it's also not completely chaotic. It is on a line here. We have tons of other examples of this. We're currently working on a larger scale validation of these type of assumptions for like 10 plus replication studies, but I don't have enough time here. So I was very happy to see this because this means that the shift on like replication studies, at least for this one, is not adversarial. There seems to be some structure that we can exploit for inference. Okay, inference. So we want to construct confidence intervals that take into account both types of uncertainty, the sampling uncertainty and the random shift uncertainty. We need to now estimate the delta. So essentially like how strong the random shift is. And you can't just do bootstrap here because bootstrap just mimics the IID sampling. So that would just give you confidence intervals that are far too small, right? So that idea does not work. Just data splitting does not work. Actually, no assumptions. Delta is not identifiable. So now the stability idea comes into play. So maybe you have like a scientific reason to believe that for the original distribution, you don't just have one estimator for the causal effect, but maybe multiple ones, maybe a regression adjustment, maybe instrumental variable approach, maybe something else. And you would say like, well, if I had infinite data, there's a scientific reason to believe that these estimators would be the same. If that is violated, we will later get overcoverage, but this is kind of what you try to achieve if you select different estimators. And now what you can do is, in our model, you can estimate this like inflation factor by essentially looking at the between estimator variation. So the estimators that you think are reasonable divided by essentially the expected variation that you would have under IID sampling. So you get an inflation factor. It might be large, it might be small. And then you can build confidence intervals by taking your estimator as usual, plus minus some quantiles, square root variance divided by square root of n, but then you have this additional variance inflation factor here that is coming from your stability analysis, okay, from all of those multiple reasonable estimators that you have. Okay, a bunch of takeaways. I don't have much time, so I'll go about it like relatively briefly. Based on this, you can give recommendations for like a good stability and a bad stability analysis. A bad stability analysis is if someone just computes the same estimator 10 times, says, okay, they all agree, I have a ton of evidence here, okay? So that's not very convincing. That would not work in our setup because in that case, you would divide by 0 here. So our estimate, if you just report a bunch of estimators that look similar and say, oh, they all agree, I'm sure like the result holds, this method will penalize you because they're like too correlated. So ideally, what you should bring is estimators that really kind of are based on different scientific assumptions or estimators that are uncorrelated. This is similar as in Rosenbaum's evidence factors. He also says that you should construct independent sources of evidence based on a single data set. You can summarize everything in a single number based on this framework. And yes, if delta is high, there are regimes, for example, where sampling uncertainty is of little importance compared to distributional uncertainty. So I think that is important for us statisticians. We often think like, oh, I just do plus minus 1.96 divided by square root of n times standard deviation, and this is my uncertainty. But I think there are a lot of cases in the real world where like the random distribution shift or some other issues are just of far larger importance. And I think it's important that we know in which situation we are. Okay, summary. We've seen some evidence for dense distributional shift. So that was the QQ plot that I've showed you. These shifts then lead to discrepancies that look larger than what you would see under IID sampling. I think we've also seen a bunch of examples earlier in the replication studies. There are different ways of kind of capturing this variation. Ideally, you'd run a ton of replication studies, but maybe some of the variation you can also already capture with a stability analysis. And I've given this talk at other venues, and at some point someone came to me and said like, well, one way to think about is like, are you just doing a meta-analysis on a single data set? I'm not sure that is the best way of putting it. This is one way of thinking about this because we're still essentially our variance inflation is a between estimator variation similar to what you would do in a meta-analysis. It's just that these estimators are coming from a single data set. Okay. All right. Yeah. Thanks for your attention. Let me know.
The time management was again excellent. We have plenty of time for questions.
Great talk, Dominik. So can you try to make a connection between what you're doing with what Maya's talk, right? She had a lot of replication analysis, right?
I would absolutely love to run the diagnostics that I showed you before on those data sets. What I'm personally interested in is like first learning for the type of like replication studies that we've seen in Maya's talk. Is it a dense shift? Is it a sparse shift? Is it sparse plus dense shift? We have ways to diagnose that. So yeah, I would also like to like have a look at that and see whether we can debug that further.
So the QQ plot, it's really interesting and kind of matches your asymptotic normality stuff. But that's, for me, is consistency, right? There might be other ways that you won't see the fit. So can you develop more kind of checking than just, this good is consistent, right? It's the first step.
Yeah.
But it would be interesting to maybe even take context with Peter's talk to really have other ways which fit into the context to see whether your model or devise new kind of stability models that people can devise. It's more like go for a paradigm instead of just, here's my model.
Yes,
like,
yes.
If I have this situation, can I follow these steps to come up with a reasonable model that captures something?
Yeah, that's a fantastic point. So one of our long-term dreams here is that, like, so in the end, this thing is like, it's a model and it's fixed. And I think it will just be like a building block in a whole pipeline. So the way that I'm currently thinking about it, this is a model for essentially distributional noise. It's a very simple model, but maybe for example, you have a sparse shift in covariate age, and then like a dense shift in the residual ones. Or maybe you have two dense shifts on top of each other, like with different size based on X, one on Y, right? So that what we want is diagnostics where you can really like look at the data. First, like, you see a sparse shift, you remove that. Now you look at the residuals again. Now maybe you see a dense shift in X, and then look again, okay, is Y given X shift different from that? So we like an entire pipeline where you can like diagnose distributional shifts in a hierarchical fashion and then build more complicated distributional shift models where this is just a module of it, essentially. That's
and also throw in the spatial dependence.
Yes. Yeah.
Hi, great talk. Can't wait to talk to you back at Stanford. So at the beginning, maybe I got this wrong. You said there was a connection with causal inference that you were going to make. Did I miss that?
So I've done a lot of causal inference research before, so that's the natural example that I had in my head when I kind of, So I thought like maybe, so in causal inference, often like you have an observational data set, maybe you have multiple identifying assumptions that might seem reasonable on the same data set. You could run regression adjustment based on a set of confounder, maybe regression adjustment based on another set of confounders, maybe like there's an instrumental variable, maybe DID, maybe a regression discontinuity design. So
I see. So this could be the beginning of that connection between the stability concept and the causal inference, which we mentioned earlier. Would you say that?
Yes. I like one thing that like about so here, like for the causal inference community, we're protecting it against something very particular. We are protecting against random shifts. In the causal inference community, people are most often worried about confounders, and whether confounders are well approximated a random shift is not clear. I think people often think about confounders as like they want like sensitivity analysis. They want to do it in a worst case fashion. So I think there might be some cultural steps or things that we would have to first go through before.
Cultural, but not mathematical.
Not necessarily mathematical.
Okay, well, we can deal with the cultural. Okay, thanks.
Okay.
So if I understood you right, kind of the core idea is you set up distribution over distributional shifts, right? And you have one way to do that. It leads to this great asymptotic and estimable framework, but there are other ways to do that. So for example, hierarchical Dirichlet processes. It's kind of on the other end of the cultural statistical spectrum. Could you just contrast these two approaches or other similar approaches for creating random hierarchies of distributional shifts?
I think that like generally speaking, you can ask about the connection to like, let's say hierarchical models, right? I think hierarchical models are quite often used if you have tons of data sets, right? And then you have maybe a structure based on observed variables. Here, I think the main competitor for us is, or like the main things that we want to extend are distribution shift models. So where you only have one or maybe two distribution, and that's the end of it. So you don't have enough structure to write down a fully like a hierarchical model, but maybe you can rely on some other structure, some symmetry structure, as in here. But like there are like far more connections than that. So for example, there are some. You can think about this random like shifting also like as a sort of a prior. It's a type, So there are, So these type of mathematical structure that we have here also kind of pops up in Bayesian statistics if you choose your prior properly. Yeah.
Thank you. All right, that's about time for questions. So let's thank our speaker again.